Last week we found that strain gauges change the resistance a very small amount when they're stretched. So we'll need some kind of a system to allow us to detect that small change in resistance. And one of those approaches is the Wheatstone Bridge. So we'll do some more measurements with strain gauges later on, but this week I want to give you at least a brief introduction so you can start thinking about how we can process analog signals in order to get better measurements from them. The basic idea of a strain gauge is that if you take an element of material and you stretch it, it's going to be subject to strain. And there's Poisson's ratio involved, which you'll learn more about in solid mechanics. And that governs how much the section here is going to get narrower because it gets longer. So it's not a simple relationship, but it works out okay. And in materials, you'll find that a typical stress-strain curve for mild steel looks something like this. It's elastic. As we stretch it out, we're straining it in this direction, so as we stretch it out, it gets longer and longer elastically, and it'll bounce back. But eventually it yields. It bends permanently at a given stress, and it will never bounce back after that. So we're usually quite interested in stress and strain, but in this course we're going to be interested in them mostly so that we can measure loads with load cells and things like that. But the key thing here is that strain is the fractional elongation, and it's usually measured in microstrain, that is micrometers per meter, or similar sorts of units, the fractional elongation of whatever we're looking at. Now, if we have a bar of metal and we stretch it, its resistance is going to change. It's going to change for multiple different reasons. One is if we make the bar longer, the resistance is going to be higher. If we make the bar narrower, smaller transverse area, the resistance is going to be higher. Or if it's bigger, the resistance is going to be lower. And so we can apply that technique. If we apply a load to the bar, then we'll have strain increasing the length and decreasing the diameter due to Poisson's ratio, and it's going to distort the crystal structure, changing the resistivity. So you'll have piezoresistive effects. And all of those are going to increase the resistance of the bar if we stretch it, or decrease the resistance of the bar if we compress it. So as a bottom line, the change in resistance is proportional to the change in length. So we can use that change in resistance to measure how much the length changes. And we'll measure small changes in resistance relative to the original resistance and small changes in length relative to the original length, which happens to be, by definition, the strain of the material. And those two are going to turn out to be proportional. And what we'll do that with is a foil strain gauge. And you looked at one last week. If you looked closely, you would have seen two fairly large tabs here for wires to connect to so that we could put it into a circuit. And then some little tiny lines going back and forth. These are the resistance elements. These are the bars. This electrical resistance of a bar of metal, these are like a bunch of tiny little bars that we're going to stretch in this direction. So we're going to have these thin sensitive elements that are oriented vertically. And up at the ends here, just zooming in on this region, you'll see that we've got, for the horizontal parts of the gauge, we've got really thick loops here. So they're going to be relatively insensitive. Yes, if there is some stretching in the horizontal direction, these components will stretch, but their resistance is going to stay really low. So you measured with a foil strain gauge, you found that it didn't change resistance very much, but it did change resistance as you bent the bar. The amount that the resistance changes relative to the amount that the length changes is called the gauge factor, and it's provided by the manufacturer. And it's a combination of all three of those effects that we saw: increase in length, decrease in diameter, and the crystal structure distortion. It's usually right around a factor of 2. So 2.08 plus or minus 1% for this particular collection of strain gauges, and that's the ratio between the resistance change and the strain change. So the change in resistance will be typically about twice as big as the change in length. So how big is that resistance change going to be? Well, the maximum possible load of interest in non-destructive testing is going to be when we would be getting up towards the yield strength of the material. We don't want to bend things permanently. So we're looking at only about 1 part in 1,000 change in the size of something. So very small changes in size. That'll result in about twice as large a change in resistance. So if our gauge factor is about 2, we'll wind up with a change of about 0.02 ohms per ohm. Or if we had a 100 ohm strain gauge, it would rise up to about 100.2 ohms or drop down to about 99.8 ohms. So a very small change in resistance. And how are we going to be able to measure that? Well, we looked at voltage dividers last time, and if we put our strain gauge into a voltage divider, we could measure this voltage V, and it's going to depend on the ratio of the resistances. And if R1 is our strain gauge and it's about 100 ohms and R2 is 100 ohms, then this voltage is going to be 2.5 volts in between, if they're exactly equal. If we see a small change in the resistance R1, we might go a little bigger than 2.5 volts or a little smaller than 2.5 volts. But to see what's going on here, we'd have to be measuring out at the 4th decimal place. And that's going to be difficult. So really hard to resolve if we're measuring on our 5-volt measurement scale on our multimeter. We can solve that problem by taking our resistance R1 and putting it into a circuit that's known as a Wheatstone Bridge with a total of 4 resistances. Now very often you'll see them drawn like this. I find it hard to draw these ones because I always get them out of whack and don't get the edges even. And this I find easier to understand. If we had plus 5 volts up here for our power supply and ground down here at 0 volts, then we've got a voltage divider just like we had before with R1 and R2, and we've got a voltage VA in between just like we had before with R1 and R2, and it's about 2.5 volts. And if R3 and R4 are just the same, this will be 2.5 volts as well. So if they're all equal, then VA is going to be equal to VB, about equal to the supply voltage divided by 2. However, if any of these resistances changes, even by a tiny bit, one of these voltages will change by a tiny bit, and we'll be able to measure that difference in between them. And we'll be able to measure that distance on that difference on a low voltage scale. So we can basically, by taking the difference between VA and VB, we can get this 2.5 volt part to cancel out. So we'll get rid of the 2.5 volts there and the 2.5 volts there, and we'll just be left with 1.25 millivolts and negative 1.25 millivolts there. So we'd wind up with something that we can measure on a millivolt scale fairly accurately, and even more accurately if we amplify that result. So the idea with this Wheatstone Bridge is to use a clever arrangement of circuit elements to be able to isolate this resistance change in R1 as a difference between these two voltages and make it a little easier to measure. So try this in a Jupyter notebook just to see how linear that behavior is, because we hope it's going to be linear.